Good evening, everyone.
Evening, boss.
Please, I'm sharing my screen. I hope you can see my screen.
Yeah, you can see your screen, sir.
Okay, that's great. So we'll be working on solving some questions. Maybe solving some questions and other things that we've done so far. All right. So I told you that from next week Monday to next week Saturday, we'll be having DCIT 203 every day. And the goal is to be able to prepare or ensure that everyone is very well prepared. I mean, in all manners possible, both in slides and understanding how questions might appear or how to answer questions before the paper on Sunday. So that is what we will be doing. So today we are going to solve questions on everything done so far. I am not sure whether the others will be joining or if we should allow or wait for them to come in or we should begin. So what do we think? Should we allow some
Yeah,
time?
we
Please,
should begin, sir. We should begin, sir.
we should begin. All right.
Yeah, because the recordings will be available.
Yeah, we
Okay.
should start. We should start because the time too.
All right. That's fine. Please, can you see the slides as well? Please, can you see my the slides that I'm sharing currently? Please, can you see that?
Yeah, you can see your screen, sir.
Yeah. I'm sharing some slides currently. Can you see that one also?
Yeah, you can see
Yes.
all good, all good.
Okay. So here we are. So we'll be looking or we'll be solving questions under digital circuit. So under combinational circuit, the first type of circuit that we studied was the adders. So at the first batch of questions, we'll look at questions on adders. And then when we are done, we solve questions on comparators also. And then when we are done, we solve questions on multiplexers, and then hopefully we can end today's session. So let's start. So when I'm done, I'll share the sites with you. So this is a site that houses question banks for computer science courses. That is university grade question banks for computer science courses. And most of the courses that we are doing, you can be able to get MCQs, question banks to them for your own study and practice. And they are organized into topics. So each topics you can find question banks under them. They also offer tests, they offer courses and a whole lot of things, okay, certification courses, etc., etc. So you can take them all here. So when I'm done, I'm going to share the link with you so that at your own leisure time, you can also practice. The interesting thing is that after going through the question, you can click view answer here. So you get to see the answer and then a short explanation for the answer there, which can really help you in your personal prep. So let's move straight away to the question. So I'll read the question and then we allow one person to answer, and then we all provide a standard solution to the question. So question 1, in parts of the processor, others are used to calculate. So in parts of the processor, others are used to calculate A, addresses, B, table indices, C, increment and decrement operators, and D, all of the mentioned. So do we go for A, do we go for B, do we go for C, or we go for D? Yes.
I've never seen this question before.
I'm not supposed to see. Question. Please come again.
I'm going with C.
C. Okay, so
I'm going for D.
okay.
I'll also go for D.
Okay, so those going for C, can you tell us why C, and those going for D? It's a discussion actually. We want to make sure that before we leave here, we don't just go through questions, but we understand the concepts behind the questions, so that even if we have a similar concept examined in another manner, we are still able to apply the same understanding to solve it. So yes, please, those who went for C, can you tell us why? Yes. So why increment and decrement operators?
The question is asking about others. What others are used to calculate? So I think arithmetic operations. In my point of view, I was going to go for, if we had addition, I would go for addition, but we don't have addition. That's why I'm going for increment and decrement.
Okay. Okay. All right. So those who went for D, can you also tell us something? Yeah. So why all of them mentioned? Why all of them mentioned?
Okay, so I'll choose D because others are used for just to perform addition of binary numbers. So
Okay.
and it can be also be used to you can get a truth table from it. You can increase and decrease operations and all that. So I chose D.
All right. All right. So that's a nice so the correct answer is actually D. Okay. And it's not difficult to know this is D because of option A specifically. Okay, so others are employed in memory addressing. Oh yes. Meba why meba cho. Meba cho. Sorry. So let's continue. So the option is option D. So and we said that and basically the easiest way to identify these correct is because of the A. Okay. So others are sometimes used in memory addressing. So when let's say there is an increment in memory, etc., it is others and stuff that are used to calculate those new things. So if you recall very well, under DCIT 207, you see how memory interacts with inputs, changes, etc., etc. And others are employed to make those happen. So yes, increments and decrement operators are very true. In fact, those are the basic functionalities of others. But others are also used for other things like memory addressing or for addresses. They are also used in table indices, etc., etc. All right. So the best answer for this question is our option A. So let's look at question 2. The total number of inputs in a half adder is. So the total number of inputs in a half adder is.
That would be A.
So A, all right, 2 inputs. So any other answer?
A.
All right, so we all agree it's A. All right, so if we go back to our others, let me show you something, right? Exactly. So this is a half adder. We said that a half adder, the behavior of a half adder, okay, or from the block diagram, we said that it takes two inputs in the form of X and then Y, and then returns an output in the form of sum and then carry. So option A is correct. It takes two inputs. So if you have to view an answer, you can see that option A is correct. So let's look at question 3. Question 3. In which operation is carry obtained? So in which operation is carry obtained? We have A, subtraction, B, addition, C, multiplication, and D, both addition and subtraction. In which operation is carry obtained? Yes.
A.
A, okay, someone is saying subtraction, yes.
Sorry, I meant B. I meant B.
Meant B, okay. So you are going for B, all right. So is anyone else going for something else? Okay, so
Addition.
A is truly addition, correct? So if you check from the block diagram of a half adder, we can see that here, that it returns sum and then carry. Okay, so carry is the second input of an adder. So it is an addition operation. So question 4, if A and B are input of a half adder, the sum is given by, so this gets a little bit technical. Let's look at the question carefully. If A and B are inputs of a half adder, the sum is given by A and B, B, A or B, C, A, X or B, and D, A, X nor B.
Hello, sorry. My network dropped. What was the answer for question 3?
Question 3, the answer was B, addition. The answer was B, addition. Because you said that if you go to our diagram, carry is a characteristic of adders. I mean, half adders, full adders specifically. Okay, so when we go to subtractors, we don't use carry. We rather use borrow instead. So we are now at question 4. If A and B are inputs of a half adder, the sum is given by A and B, B, A or B, C, A, X or B, and D, A, X nor B.
I think you see A, X, or B.
A or B.
All right, so any other person?
So B. A or B.
The same one. C.
All right, so
C, A,
someone
X,
is
or B.
saying A or B. Oh, let's feel free. Okay. So when you're done, you look at what the slides also see. All right.
I think it's C, A, X, or B.
All right. So let's clarify from the slides. Oh, this thing is okay. So let's clarify from the slides. So this is the truth table for a half adder. And let's look at minimization. So the question said that the sum, right? So you can see right here that the sum is an A, X, or B operation. Please, can you all see that here? That the sum of a half adder gives us A, X, or B. So you can see that right here. The sum is equal to A, X or B? And please, do you all know why it's A, X, or B? Or should I explain it properly?
I know, sir.
So we can move on.
We can move on. All right. So let's move on. Question 5. If A and B are inputs of a half adder, the carry is given by. If A and B are inputs of a half adder, the carry is given by A and B, B, A or B, C, A, X or B, and then D, A, X nor B.
A
and B.
All right, so please, do you all agree with that?
Yeah.
Yes, sir.
All right, exactly. So if we check the carry, we can see that the carry is A and B. So it's a AND operation of A and B. So that means that our answer is truly A. So let's go to question 6. Half adders have a major limitation in that they cannot A, accept a carry bit from a present stage, B, accept a carry bit from a next stage, C, accept a carry bit from a previous stage, and D, accept a carry bit from the following stages. So what are we settling for?
I'll go for A.
All right, so accept a carry bit from the present stage, okay. So who else have a different opinion? Yes. Please, are we all also choosing A? Are we all choosing A?
So still thinking about it.
Okay, so let me give you a moment to think about this question properly. Okay. All right, so
Please go back to the answer. Yeah,
okay. So is anyone else choosing anything else before we clarify from the slides?
I think it's previous stage.
let's go B.
Okay. B from a next
I'll go
stage.
for
All
C.
right, so okay, so let's go from let's look at full adder. If we look at full adder, we can be able to see something here. Okay, so we said that the full adder consists of 3 inputs and 2 outputs. It can add 2 1-bit numbers A and B and a carry C. So let's look at the carry that full adders work with. So you can see that full adders, they carry in inputs from previous operations. And that is the limitation of a half adder, which makes the development of a full adder necessary, or which necessitated the development of a full adder. Half adders cannot accept carry in. So if there is a carry in from a previous operation, half adders cannot work with it. All right, so that is a major limitation of a half adder. It cannot accept a carry bit from a previous operation. It only works with its present inputs only, but cannot accept carry bits from a previous operation because it takes only 2 inputs. So if a carry bit comes in, you have to get 3 inputs instead. All right. Meanwhile, a half adder only has 2 inputs. So that's here. You can see that a half adder has only 2 inputs, X and Y. So if there is a carry coming from the previous operation, a half adder cannot perform that operation. So the correct answer is C. Half adders cannot accept a carry bit from the previous stage or operation. All right, and if you check, you can see that that is C. So let's go to question 7. Question 7. The difference between half adders and full adder is A. Half adder has 2 inputs, while full adder has 4 inputs. B. Half adder has 2 inputs, while full adder has 2 inputs. C. Half adder has 2 inputs, while full adder has 3 inputs. And D. All of them mentioned. So what are we settling on?
C.
C.
Two,
All right, C is
two
correct.
inputs and 3.
Yes, C.
Exactly. If we check from our slides, you can see this is a half adder. Half adders would take exactly 2 inputs, which is X and then Y. And let us check for full adders. You can see full adder here. Full adder takes 3 inputs, A, B, and then our carry in. So the C is correct. Half adder takes 2 inputs, whereas full adders take 3 inputs. Let's go to question 8. If A, B, and C are the inputs of a full adder, then the sum is giving us, please, let's look at this question very, very carefully. If A, B, and C are the inputs of a full adder, then the carry is giving us A and B, or into brackets A or B and C. B, A or B, or brackets A and B, and then C. Then C, A and B, brackets, or A and B, and then C. And then D, A, X or B, X or A, X or B, and C. No, I've skipped question A, sorry. If A and B are the input of a full adder, then the sum is given by, please, I've skipped the options. A and B and C. B, A or B and C. C, A, X or B, X or C. And D, A or B or C. So which of these correctly represents the sum of a full adder?
A
C.
or B or
Okay, so someone
Yeah, I
said
think they
A
are
or
all
B.
plus. So A or B or C.
All right, so A or B or C. Okay.
I'm going with
So
A,
any,
X or B, X or C.
all right, so please, who said A, X or B, X or C? Can you tell us why?
So
Okay.
I think I remember that when we had an assignment that he gave us to construct a full adder, and then that is what I had after drawing my truth table. That's why I'm saying A, X or B, X or C.
Okay, so that's a very, very, very good observation that you did, because that's actually correct. We said that for a half adder, the sum is A, X or B. Okay. Now a full adder, the sum, since you have 3 inputs, A, B, and C, it's just the same thing as the sum, but we are going to take one more X or of our third input, which is going to be A, X or B, X or C. Let us look at this right here. So you can see this here. So you can see that sum is equal to, you have A, X or B right here. I'm trying to, so sum is equal to A, X or B, X or C, and your C is your C in, okay, or C input. So your sum is A, X or B, X or C, which correctly reflects C. So, and your corresponding carry is going to be A and B or B and C in, or A and C in. If you joined the class where we treated others, you should be able to recall all this, okay? So C is our correct answer here. Then question 9, if A, B, and C are input of a full adder, then the carry is given as, if A, B, and C are the input of a full adder, then the carry is given as, yes, A and B, or A or B and C. Then B, we have A or B or A and C, A and B, and then C. And then C, we have A and D, or A and B. Then we have C. And then last one, we have A, X or B, X or A, X or B, and then C. So please, which one is our correct answer? So what's our correct answer here?
A.
Okay, so you are going for A. All right. That's very nice. So can you tell us why A?
As for this one there, I'm doing this one. What do you call it? Guessing.
Okay. Okay. So let's look at what is here. I want us to expand this, and then we are going to see something very interesting here. Oh, I still have yesterday's. Yeah. All right. So let's expand the option here. So we have option A. We have A and B. So we have A and B. This is A and B. Please, you all agree with me, right? And then we have or.
Yes, sir.
So let's write our or. Then we have brackets. Then we have our A or B. So that is A or B. Then let's come back and C. So we have and C. So if we open our brackets, we are going to have A dot B plus, we are going to have AC, which is A dot C plus B dot C. Please, you all agree with me that this is the expanded form of this.
Yes, sir.
All right, so now let's go back to our slides and then see which, what is the carry expression? What is the expression for a carry for a full adder? You see that our carry expression is A dot B. So if you check here, we have what? A dot B plus B dot C. So you can see that we have plus, you can see your B dot C, then plus A dot C. You can see that you have your plus A dot C. So please, have you all seen this right here? Please. So this is the correct carry expression for our full adder, and that corresponds to option A, which are rather rightly selected. So the key to getting the answer is knowing the expression for the carry of a full adder and being able to identify it in the options below, even though it had been represented in this form. If you just expand, you will be able to just deduce that directly. Okay. So the simplest way of remembering or capturing the logic expression for the carry of a full adder is that it is just made up of all the alphabets in your input, which is A, B, and C, but they are arranged in a form A dot B. Then we have plus, then we have B dot C. Then we have plus A dot C. All right, so this is basically how it works. So you have A dot B plus B dot C plus A dot C. That's a carry for a full adder. And then the sum, you are going to have A X or B, X or C.
This is the hand.
X or C. Please come again.
There's a hand up.
All right. So I'm coming. Yeah, Mr. Joshua, we are with you.
I was saying there was an hand up. There was an hand up.
Yeah. I think
Sorry, it was a mistake. It wasn't intentional.
Oh, okay. So that is how to memorize that. All right. So we can move on. So let me show you something at a full adder. Once you're able to memorize full adder, half adder is also very similar. You can easily memorize that also. You can see that the expressions are almost similar. So for half adder, your inputs are just A and B. So then the carry is just going to be A dot B. And then for the full adder, it's going to be A, X, or B. All right. So when you are dealing with a full adder, then you know that a new input is introduced, which is C. So you add one more XOR for the new input, which is C. And then for the carry, you know that one more input is C has been introduced. So you perform the combination for that, which is A and then C plus then B and then C. And that gives you your full adder. So you should be able to recall this. So let's go to question 10. So question 10 is saying that how many AND, OR, and XOR gates are required for the configuration of a full adder? How many AND, OR, and XOR gates are required for the configuration of a full adder? Yes. What is the answer?
I don't think the answer is here.
Oh, okay. So you said you don't think the answer is there.
Because
All
we should have two XOR gates. Okay, let me see the question again.
Okay. So how many AND, OR, and XOR gates are required for the configuration of a full adder?
Okay, so we
That's
need
what I'll get to.
I think three.
All right. So we said 3 what?
I think 3 AND gates.
Okay. So someone said 3 AND gates. Let's write that down before we look at the correct answer. So someone said 3 AND. So 3 AND gates.
And 1 XOR gate.
And 1 XOR gates.
And 1 OR gate.
And 1 OR gates. Okay. Well, that's okay. That's okay. So anyone with another.
Yes. So I am saying we would need for full adder we will need 2 XOR gates.
So 2 XOR gates.
Then 3 AND gates.
3 AND gates.
And then 2 OR gates.
And then 2 OR gates. Okay. So any other submission? Any other submission? All right, so let us check what the slides have to say with regards to this very question. All right, so from the slides we have one XOR gate here. We have 3 AND gates. So the slice is given as 3 AND gates. 1 XOR gates. And then 1 OR gates. This is what the slide is giving us. Okay. So let's see if it corresponds to any of the answers there. No, unfortunately, it does not correspond to any of the answers there.
All
right.
hello.
So, yes, sir.
So you see, what if you decide to draw? Draw this circuit in a different way. Because I remember the last time the lecture was like, we don't have any wrong way of drawing this thing, provided you have a equation. You can choose to draw it any other way. So, like I was saying, what if I decide to do first A XOR B, and I connect that one, I connect the output to another XOR gate with the C.
Okay.
You get me?
Okay.
Then I do same for the OR gates. So A B connecting to one OR gate, B C connecting to one OR gate, then A C connecting to another OR gate. Then the output, I'll connect two of the first output. The first two outputs to one OR gate, and then the output of that very one together with the third output. What about that one?
All right.
Is that wrong, or you're saying you're going
All
to?
right. So, I think personally, I would agree with the notion that there isn't one definite way to represent your circuit diagram. Okay. And looking at this, there are typically several ways that this can be represented, giving you expression A X or B X or C. Okay. Someone can even decide to represent this way differently. Okay, so the slide they decided to use 1x or to implement this 3, which is very correct. So, and then you have here you have a product term here, a product term here, a product term here. And so here they used an and, another and. So here we have 2 XOR. Okay, so 1 XOR here. But then you can decide to implement all this according to the slides. They implemented this XOR and this XOR with just 1 XOR and connected all the 3 inputs to that 1 XOR. So they use that's how come they had 1 XOR here. And here is an and and another and. Hence 3 different ands right here. And then they connected since it's an SOP, okay, sum of products. The 3 product terms are being summed together. So they used an OR gate to perform the summation operation, which is also very correct. And as our brother rightly said, there are several other methods to represent this. So in my own terms, I've thought that this question is quite ambiguous. Okay, since it might most likely depend on how one might want to represent it's. However, let's see which answer they selected. Okay, they went for B, two AND gates, 1 OR gates, and then 2 XOR gates. Okay. So let me see.
Say please, what is the actual answer?
the actual answer they gave was B, which is 2 and 1 OR and 2 XORs. So you see what I was saying. So it means that this XOR, they used a different XOR to implement this and a different XOR to implement this. And then if you use two different XOR to implement this, then you still have to combine those XOR together. Okay, you still have to combine the XOR together, but you cannot leave them hanging like that, which will lead to another gate altogether. But even if they did it that way, I don't think they get to let me see. I don't think they'll get two AND gates. Because if they did that way, the case of your AND gates, here you have 3, 1, 2, 3. And I don't know how they went. Okay. I don't know how they went about this, except if they represented the expression as they did right here. So if they represented the expression like what they did here, then that will make a little sense for their option for an answer. All right, so Formula 4, this question is quite ambiguous, okay, as it is totally dependent on how one prefers to draw the truth table for a full adder. Okay. All right, so that brings us to the end of that set. So let's move to the next sets. All right, so let's go to the part 2 of our half adder truths adder question set. So this question says that the set of digital electronics or one for this set, we have half subtractor is used to perform the subtraction of A, 2 bits, B, 3 bits, C, 4 bits, and then D, 5 bits.
2 bits.
2 bits.
All right, so we all agree with 2 bits, right? So if we come down in our slice and we look at subtractors, you can see half subtractors here. It takes only 2 bits as inputs, which is your A and B. Hence, A for an option is completely justified. So let's go to question 2. So let's go to question 2. Question 2 is saying that for subtracting 1 from 0, we used to take a dash from neighboring bits. Okay, the English. So from taking 1 from 0, we use to take a dash from neighboring bits. Well, so A, we have carry, B, we have borrow, C, D, we have outputs. So if you are subtracting 1 from 0, you know that isn't possible. You can rather subtract 0 from 1. But taking 1 from 0, you know that in subtraction, we do something from the neighboring bit. And what is that called? A, carry, B, borrow, C, inputs, and D, output. Yes. Yes, what are you going for?
It will be B, borrow.
B. All right.
Yeah,
So
borrow.
please, do you all agree it's B?
Yeah, I agree with you.
Do you all agree it's B? Please, I believe we all agree. All right, so that's B right there. Because whenever you are performing subtraction and we are subtracting something like 0 minus 1, okay, so we are subtracting something like, let's say we have 1, 1, we have, let's say 1, 0 right here. No, let me write this properly. So we have 1, 0, and then we have something like 1 right here. So this the right bits operation is going to give us that is the LSB operations for both is going to give us something like 0 minus 1. Okay, so with this kind of operation, we know that we have to borrow, right, from this place. So whenever we are performing subtraction and we encounter such a problem, we do what? We borrow. Okay, so in the case of subtractors, like half subtractor, full subtractor, we always borrow. But unfortunately, half subtractors cannot perform borrow operations, so we use full subtractor for that. So let us come back. So B is our correct answer for this. So question 3, how many inputs are required for the implementation of a subtractor? I think we looked at a similar question. So we said 2, right? Yeah. So let's move on. All right. So let the input of a subtractor be A and B. Then what will be the output, or what will the output be if A equals B? Wow, a very, very interesting question. So let's look at the question carefully and thoroughly. So the input of a subtractor is A and B. What will be the output if A equals B? So can we work this out? So the inputs of a subtractor is A and then B. So what is going to be the output of that particular subtractor if A equals B? So let us work this out. So what do we think the answer is going to be? A 0, B 1, C A, and then D B. Yes. Monica, will you help us out? All right, so would anyone give this a try? Or he wants us to explain?
It's tricky.
One.
All right,
The
so
question is
someone will come in.
I was saying the question is tricky.
It's tricky. Okay, so it's actually not two. Let's look at this. If someone went for 1, so let's verify the answer. So we are dealing with a subtractor right here, okay? And then they are saying that the two inputs are A and B, and then A and B are equal. So we know that A and B are equal when A equals 0 in terms of binary numbers, where A equals 0 and B equals 0. Or you can also say A and B are equal when A equals 1 and then B equals 1. So they are asking, what is going to be A minus B? Okay, because you know that a subtractor performs a subtraction operation. So if this is our inputs, then what is going to be A minus B? So let's take the first case. If A is 0 and B is 0, we are going to have 0 minus 0. That still gives us a 0. Let's take the second case. If A is equal to 1 and B is equal to 1, that is going to be 1 minus 1. So that's a 0. So whenever we have a subtraction operation involving 2 bits, such as A and B, and both inputs are equal, regardless of the circumstances, the final output will also always be 0. It means you are subtracting 2 numbers that are equal. Okay, your corresponding answer will always be 0. Please, do we understand the question? Please, do we understand the question now, or you think I can take it again? Hello. We are okay. All right. All right.
Yeah, it's
So
clear.
let's go
It's
to
clear.
question. Okay, so let's go to question 5. So question 5, let A and B be the input of a subtractor, or if A and B is the input of a subtractor, then the output will be, I think there is a typo error in there. So if A and B is the input of a subtractor, then the output will be A, X or B, A and B, C, A or B, and then D, X nor B. Yes. Yes. So what do you think is going to be the answer for 5? So if A and B,
AX or B.
AX or B, all right. So that's a very, very interesting answer for us right here. So please, does anyone have any contrary answer? And then let's look at that from the slides. I mean, let's clarify that from the slides. So you can see that the difference, as the question is asking. So if A and B, the output will be, which is the difference, okay, is here. So here in the slide, they use X and Y. So you can see that the difference is X prime Y plus X Y prime. And we said this right here is the same as X or Y. Please, this was one of the first concepts we established when we were looking at adders and subtractors. We said that if you have any instance where you have something like AB plus AB, but then in the first AB, the A is prime, and in the second AB, the B rather is prime, we said the resultant is an XOR operation of your two inputs in that expression, which is A, X, or B. So here you have XY, and then X is prime in the first product term. And in the second product term, your Y is rather prime. Then it's going to be the XOR of X and Y. So you can see that the difference of a subtraction operation using a subtractor is X or Y, or A, X, or B. Hence, A is a correct answer. Hence, A becomes our correct answer. So let's kindly take note of these. So question 6. Let A, no. Yeah, so question 6. If A and B is the input of a subtractor, then the borrow will be, if A and B is the input of a subtractor, then the borrow will be A and B prime, B, A prime and B, C, A or B, and D, A and B. What is going to be our answer?
A prime and B.
A prime and B. Okay, so we are going for option B. Anyone with a different idea? Before we look at the slides. All right, let's look at what the slides is saying. So if we are talking about the borrow, we know we have X prime and Y, okay, to be our borrow. So let's come and check here. you can see that we have A prime and B. Okay, as our brother rightly indicated, will be our answer for that. And I believe we should all know how to deduce this by now, or how this came into place by now, because we've actually done it in our previous sessions. So question 7. What does minuend and subtrahend denote in a subtractor? So what does minuend and subtrahend denotes in a subtractor? So A, the corresponding bits of inputs. B, its outputs. C, its inputs. And D, borrow inputs. What does minuend then subtrahend denotes in a subtractor? So please, anyone? Oh, please,
I think the
the
borrow bits.
borrow bits. Okay, someone is going for D. All right, so anyone with a contrary answer? All right, let's come back to our slides and see if it is here or it is not here. So you see, I'm sure it should be stated here. So no, let me see if it should be here. No, I think that's that. So let's take the second. Let's take the first point here and see if we'll not find an answer in there. So subtraction of two binary numbers may be accomplished by taking complements of the subtrahend and adding it to the minuend. So whenever we talk about subtrahend and minuend, we are talking about the inputs. Okay, so we said that we take the complement of the subtrahend and add it to the minuend. So we are talking about A complement and B. And what are A and B here? They are the inputs. All right, so the inputs are what we refer to as the minuend and then the subtrahend. So in this option, we are talking about option C right here. So minuend and subtrahend denotes our inputs. The first input is your minuend. The second input is your subtrahend. Are we together? All right, let's look at option A. So full subtractor is used to perform subtraction of, for this one there, I think we should all be able to answer this. So full subtractor is used to perform subtraction of, yes, A, 2 bits, B, 3 bits, C, 4 bits, D, 8 bits. Which one is the correct answer?
Three. Full subtractor. 3 bits.
3 bits. Okay. So please, do we all agree with that? All right. It looks like Monica is not talking. All right, so B is correct. We have 3 bits to be our correct answer. Because if you check from the slides, you can see that full subtractors will take 3 inputs. Your first input, your second input, and then your third input. Let's go to question 9. Yeah. So question 9, the full subtractor can be implemented using, I think we are going to have that same problem again. So the full subtractor can be implemented using 2 XOR and an OR gates, 2 half subtractors, and an OR gate, 2 multiplexers, and an AND gate, 2 comparators, and an AND gate. Yes. So let's see what the slides have for us. And the full subtractor. All right, so here we have 3 AND gates. So 3 and 1 XOR, and we have 1 OR. It's so easy. So we have the same problem here. All right, so we can conclude that this question is also very related. And then question 10, the output of a subtractor is given by if A, B, and X are the inputs. All right. So A, B, and X are the inputs. What is going to be the output of this subtractor? We can see that the inputs are 3. So the inputs are 3. Which subtractor are we talking about?
Full subtractor.
Full subtractor. So the inputs is going to be A and B, X or X. B, A, X or B, X or X. C, A or B, no X. And D, A, no B, X or X. Yes, I believe you should all get this. Yes.
A and B, X or X.
Okay, so you are going for A and B, X or X. All right, so anyone else? Anyone else? Anyone else? Anyone else? All right, so let's take this here and expand. Okay, so let's take this here for a difference. So you can see that here, if you have 3 inputs, okay, that's A, X or B, X, A, B, and B in. Then the subtraction of that operation, the difference or the corresponding difference is going to be A, X or B, X or the third input, which here is B in. So let's go back to the question. So if the inputs are A, B, and X, then the correct answer is going to be B, which is A, X or B, X or X. Then 11, the output of a full subtractor is the same as. So the outputs of a full subtractor is the same as.
This half other.
Half other. Okay. So please let's add a question again. The output of a full subtractor is the same as. So A, half adder, B, full adder, C, half subtractor, and D, decoder. So someone has gone for half adder. Anyone with another selection here. So let us look at the slides. You can see that the difference is A, X or B, right? X or B, and then X or your third input, which in this case is B in, or let's say C. So A, X or B, X or C. And now let's go to our full adder and see something. So you can see that your full adder is also the same. You have A, X or B, X or C. Please, can you all see that? Please, can you all see that?
Yeah, you can see that, sir.
Exactly. So you can see that the sum of your full adder, the expression for your sum for your full adder, is the same or is logically the same as that of a full, the sum of a full, the difference of a full subtractor. Okay, because they are all an XOR of your three inputs. And that is what this question is trying to assess. So the output of a full subtractor is the same as the output of a full adder. And the correct answer here is so we are done with this set. All right, so we are going to end the session here, and then I'll leave you to practice on your own. So please, I'm going to put a link on the platform. Kindly, if you have any leisure time tomorrow, I don't know if tomorrow, if you're able to get time, we'll meet again and we'll continue with the next set of questions. Okay. But regardless, please, at your own leisure time, kindly do well, okay, to revisit the questions that we looked at today, and then make your own assessments and analyze them better, so that the goal is not that the questions would repeat in exams, but the goal is that the same concept might be examined or is most likely to be examined, since the question bank here is a university standard question bank. Okay. So let us take our time and then go through it on our own. So I've sent the link to the platform. So let's kindly access it, and on our leisure time, we should revisit it and then try to work it out. I mean, that we've done today, try to revisit. So we've done part 1 and then part 2. So tomorrow we'll continue with the third part. So please, any questions so far? Any questions so far? Any contribution, any suggestion? I think now we are aiming to complete the slides and then solve questions under all the sections before examination. If you have any contribution in that direction, or you think there is something that you can do that will help your examination preparation, please feel free to put us forward. Feel free to put that forward. Yes. Yes. All right. So if we have nothing to say, then we can bring a closure to today's meeting and then continue hopefully tomorrow if there is time. If not, then we'll continue on Monday. All right, so have a wonderful day.
Okay, bro. Thank you very much.